Hello. In the previous module, we saw the hypothesis of de Broglie, where de Broglie had told that matters like electrons also behave like waves in certain cases. What he told was like the photons, material objects like electrons may also at some certain time behave like wave. He suggested or he proposed that if these electrons are made to pass through slits, those slits with the width comparable to that of the wavelength of the electron, then they will undergo diffraction just as photons do in the single slit experiment. This is what de Broglie postulated, and using Bragg's diffraction condition, and then experimentally it was shown by Davison and Brummer in telephone laboratories that the experimental evidence for the hypothesis of de Broglie was given, where a 54 electron volt electron was used to incident on a single crystal of nickel, where the interatomic spacing of this nickel was 2.15 angstroms, which was determined by the Bragg's law, was used, and they found that a pronounced peak was observed in the intensity. Pronounced intense peak was observed at an angle of 50 degrees. And with small corrections, they computed the wavelength, agreed to the de Broglie wavelength. And this verified the hypothesis of de Broglie. Subsequently, the neutron diffraction, low energy thermal neutron diffraction experiment was also performed, and they also upheld the hypothesis or de Broglie hypothesis. Right. So now, very important question that comes to our mind is what is waving when a massive object such as an electron exhibit wave properties? What is that which is moving or which is waving? So the probabilistic interpretation that ensues may perhaps be disturbing. In fact, it is still being debated today. However, with such an interpretation, many otherwise unexplained experimental results can be resolved. So now let's consider the interference pattern obtained in a double slit experiment with light. According to the wave picture, the intensity which is given by I, or which is the energy per unit area per unit time at a point on the screen, is given by I is equal to epsilon naught C epsilon or E square, where this E is the value of electric field at a particular point. Epsilon naught is the permittivity of free space, and C is the velocity of light. So in terms of the photon picture, on the other hand, the intensity at a point on the screen, where it's a photographic screen, right, is given by I is equal to h nu n, where h nu is nothing but the energy per photon and n is the photon flux. When I say photon flux, it means that the number of photons per unit area per unit time, which is striking a particular point on the screen. If you actually think there is no way of that we can predict in advance where an any individual photon will strike the screen. That's true, right? We cannot predict in advance where an individual photon will strike the screen, producing a single flash or making a mark on the photographic plate. Right. However, since the final pattern consists of alternating bright and dark fringes, this we know, right? So as we know, I mean, this we know that there is an alternate bright and dark band which is formed as a result of interference. So any single photon has a very high probability of arriving at the brighter band, and it's almost zero probability of the or it is zero probability that it is arriving in the dark band. So no photon will arrive in the dark band. So whereas there's a high probability that it is arriving at the bright band. So the photon flux n at a point on the screen is therefore a measure of the probability of finding the photon near that point. Okay, since we know that I is okay. Anyway, since we know that I is epsilon naught c square, which is equal to h nu. Since I is equal to epsilon naught c square, which is equal to these two equations, these two can be equated. I equal to epsilon naught c square is equal to h nu n. It follows that n is proportional to e square. N is proportional to e square. Hence, in terms of a quantum interpretation of electromagnetic radiation, the quantity that is undergoing the oscillation, namely the electric field E, is that function whose square gives a probability of finding a photon at a given place. The interference pattern described for light could have been produced with matter waves instead of light waves. Right. For this case, the probability interpretation based on the wave particle duality of light is carried over directly to explain the wave particle duality of this matter electron. So it is thus with the electron wave, the quantity oscillating with the de Broglie wavelength, with the wavelength of the wavelength de Broglie wavelength, or the with the electron wave, the quantity oscillating with the de Broglie wavelength lambda is equal to h by mv, is the wave function whose square gives the probability of finding an electron at a given place. In order to reconcile the wave and particle picture of matter, we must give up the idea that location of a single material particle can be specified exactly. Instead, we can talk only of the probability of finding a particle at a particular location at a particular time. Okay, so the wave function is wave function. When we talk about wave function, you would have seen in your quantum mechanics, or wave function is commonly denoted by psi. So for a photon, the de Broglie wave represented by psi is an electromagnetic wave. For an electron or other material body, psi is a non-electromagnetic de Broglie wave. Right. So psi is the wave function of it can be denoted for photons or for electron. okay, or other matter body. Suppose it is desired, or if we want to determine the location of a electron or a material body, in order to measure the electron's position, an experiment of some type must be performed. Okay. So, for example, a slit can be placed in the suspected path of a body moving parallel to the y-axis with energy. Okay, so let us have an electron which is moving. We have this x and y. These are just the coordinate. Say an electron is moving. Okay, in some particular direction, we have a slit, single slit, for example. Okay, so the width d is equal to delta x. We will see this. So this is the path of the electron, and we have a screen, photographic plate or a screen. This is the screen. Okay, so the electron diffraction pattern. Okay, if we see, I'll come to that, right? So so we are placing a slit in the path of a electron or a body moving parallel to the x-axis, and it has a known energy. Okay, if a mark is made by the particle on the screen placed behind the slit, this is the slit what we have. If a mark is made by the particle on the screen placed behind the slit, we will then know that the body has passed through the slit. Okay, thus the x position of the particle upon and before, or the position of the particle upon entering the slit will have been determined by an uncertainty, which is this uncertainty is given by delta x. So this uncertainty, which is delta x, is given by delta x is equal to d. The smaller we make the slit, the value becomes smaller. We make the slit wide. The smaller is the uncertainty in the x position of the body, and hence the more precisely is its location known. So as we make the slit width smaller, the smaller is the uncertainty in the x position of the body, and there is, because of which there is more, or we can more precisely locate this matter, or we can more precisely find the position of that electron. Okay, because of the wave nature of matter, the particle will be diffracted as it passes through the slit. Okay, however, even though it is not possible to predict where on screen it will strike, as long as the body strikes the screen somewhere, you know that it has gone through the slit. Right? So the diffraction process, however, has an effect on the momentum of the particle. Before the particle passes through the slit, its position was completely unknown, but its momentum was known both in magnitude. When we say both in magnitude and direction, when we say magnitude, we know in magnitude since it has a fixed energy, and direction which is perpendicular to that of the slit. So we have before passing through the slit, its position is completely unknown, but its momentum was known both in magnitude and in direction. Okay, so when the particle passes through the slit, thereby determining its position, the x component. So if you actually see the distribution when it goes through diffraction, right? So the distribution on the screen would be, we have a bright we have a bright fringe. So we have a bright fringe, then it dies down. Okay, so it's this sort of Gaussian maximum at the center. Okay, so yeah, so what we have is when with the particle pass through the slit, thereby determining its position, the x component, or px x component, or the px of its momentum may no longer be 0 because the particle will be moving towards some arbitrary point on the diffraction pattern. Because it is not known just where the particle will strike the screen, there is a corresponding uncertainty, which is delta px in the x component of its momentum when at the slit. Okay, an analysis of this shows that the uncertainty, which is delta px, can be made as small as desired by increasing the slit width d. So as we increase the slit width d, the uncertainty can be made as small as desired. Okay, however, the uncertainty in the particle's position will also increase. When we do this, we'll also increase the uncertainty in the particle's position. Right. So the uncertainty, which is delta px, can be made small. If you want to decrease the uncertainty, we can do so by increasing the slit width. And if the width we increase, there will be uncertainty in the particle's position. Okay, but the uncertainty in particle position will increase. So it is therefore seen that with a single experiment, the uncertainty in particles x position and x momentum cannot be made arbitrarily small. Accuracy is one of these quantities can be accuracy in one of these quantities can be obtained only at the expense of the accuracy of the other. You cannot determine the position and the momentum at the same time. This is what we are discussing, right? If you want the accuracy in one of these quantities can be obtained only at the expense of the accuracy of the other. If you want to determine the position, the accuracy in measure accurately, if you want to measure the position, we have the accuracy will be less when we in determining the position. If you want to precisely measure momentum, right, then the position cannot be accurately measured. Okay, so this example illustrates the Heisenberg uncertainty principle. Heisenberg uncertainty. Principle. Okay, this was first set forth in 1927 by 1927 by Heisenberg. A quantum mechanical analysis of this shows that all types of experiment, the uncertainties delta x and delta px will always be related by delta px into delta px delta x h by 4 pi 4 pi h cross by 2 pi. Okay, so in the quantum mechanical analysis, this shows that all type of experiments or for all types of experiment, the uncertainties delta x and delta px will always be greater than or equal to h by 4 pi. The Heisenberg uncertainty relation can be formulated in terms of other conjugate variables also. For example, in order to measure the energy of a body, if you want to measure the energy of a body, an experiment must be performed over a certain time interval delta t. Okay, so an analysis shows that the uncertainty in the energy, this is delta t, the uncertainty in energy delta E is related to the time interval delta t over which the energy is measured by delta E by delta t greater than or equal to h by 4 pi. Thus, the energy of a body can be known with perfect precision. When I say perfect precision, delta E is equal to 0, the change in measurement or the energy. Only this is possible only if the measurement is made over an infinite period of time. That is when delta T is equal to infinite. I repeat, energy of a body can be known with perfect precision. That E can be measured where the delta E is 0. That is possible only if the measurement is made over for a very long period of time where delta E is infinity. So the Heisenberg uncertainty principle has an important consequence for systems like excited atoms that on the average live for a finite period of time called the mean lifetime tau. Right. So tau is the mean lifetime. So Heisenberg uncertainty principle, it has important consequence for systems like atoms that which has on average a finite lifetime which is given by tau. Since the mean lifetime limits the length of time, one has to measure the energy of the system before it actually decays. The system will have a natural minimum uncertainty in their energy, which is given by delta E is equal to h by 4 pi into tau. The uncertainty principle shows that it is impossible in a single experiment to measure pairs of conjugate variables. Okay, we cannot measure the conjugate variables at given time. Both cannot be measured simultaneously. One, what we saw in x and px, which is momentum and position and momentum. Other one is E and T, energy and time. Right. So, in a single experiment, it is impossible to measure pairs of the conjugate variables to arbitrary position. So, as a result, both the particle and the wave aspect of matter cannot be measured in the same experiment. Suppose, for example, that an experiment is designed to measure the particle's property of particle property of a body, then necessarily this experiment delta x and delta t must be 0. Right? We have the change in position, then change in time must be 0, since a particle by definition can be located with infinite precision at any particular time. The position can be measured and time can be measured. The momentum and energy, and hence we have the aspect lambda is equal to h by p and nu is equal to e by h. Okay, will then, according to the uncertainty principle, be completely unknown. Okay, thus when the particle aspect of matter is displayed, the wave nature is necessarily suppressed. Likewise, if the wave aspects are measured exactly, so that delta lambda and delta nu, and therefore delta p and delta E are 0, then the particle aspect will not be observed. Okay, the inability to observe the wave and particle aspect of matter at the same time illustrate the principle of complementarily. Okay, so the inability to observe the wave and particle aspect of matter at the same time illustrates the principle of complementarity. Okay, this was enunciated in 1928 by Niels Bohr. The wave and particle aspect of matter complement each other, since both pictures are necessary to understand completely the properties of matter, but both aspects cannot be observed simultaneously.